Hello and welcome to the Architecture of Future Technology podcast. My name is Prasanna and I will be your host. I love science fiction and I'm fascinated by what the future may hold. I'm especially curious about future technology and how it's all going to work. Now, there's a story about a guy who saw how all of this technology works in the future. It's in the Bobbyverse series by Dennis Taylor. If you haven't read the Bobbyverse, go read it. Now, this guy is a software developer. He gets run over by a car. He wakes up 100 years later, and apparently his brain was preserved and copied onto some super advanced computer. That guy saw the future. I don't want to see it that way. So I'm taking a different approach. I'm going to talk to people who are working on future technology. We will try to dissect it and reverse engineer it and explore how we can go from here to there. And we will use our imagination. Thank you, Josh Groban. We will also talk science and math and technology and psychology and other subjects whose classes I may or may not have skipped in college. The first piece of future technology we will look at is autonomous vehicles. In this episode, we're going to go breadth first and get a sense of everything that needs to happen for autonomous vehicles to roam our roads. In later episodes, we will explore more specific areas in some depth. Since we're talking about the breadth of the autonomous vehicle landscape in this episode, let's start with someone who actually sees the breadth of the industry from his position as the head of software-defined vehicles at ETAS, a Bosch company. Please welcome my first guest, Joerg Seitter. Joerg, would you like to introduce yourself?
Hello, as said, my name is Joerg Seitter. I'm working at a company named ETAS. ETAS is a subsidiary of the well-known company Bosch. So I have there the role of the head of the advanced engineering, where we are looking into 3 to 5 years in the future of the vehicle technology.
Yeah, great. So this podcast is exactly about that. It's the architecture of future technology, and we're talking about autonomous vehicles. So let's say we are in the future and we're looking back, at today, 2022, and looking at what are all the things that had to happen between 2022 and this time in the future to make autonomous vehicles. But let's start by looking around in the future, and we see a lot of autonomous vehicles. So what kind of autonomous vehicles are there? Is there just kind of the autonomous vehicle, or are there a lot of different types of autonomous vehicles?
Oh, I'm pretty sure there will be lots of different types, basically starting with aerial vehicles that probably will fly, delivery drones, things like that. And then, classical vehicles, taxis, robo-taxis, maybe delivery vehicles, autonomous ships, autonomous trucks. So I think there's a lot of ways how autonomous vehicles can look like.
Is there a way that the industry classifies them?
I'm looking mainly from the automotive market on that. So in automotive, we have different systems of classification of vehicle types. Anyway, like passenger cars, like trucks and so on. Also that grade of autonomy is defined, but I'm not exactly sure how in other domains the definitions are done.
So in this future that we got to with a lot of different autonomous vehicles all over the place, was there one big problem that needed to be solved, or were there a lot of different problems in each different type of a vehicle?
I think there were and they are probably in the future. Hopefully we will have solved them all now. But even that, I'm not sure. Yeah, it's a lot of different problems. Yeah, basically at the absolute core is always the question of safety. When we build such a vehicle, how can we ensure that it does not harm anyone, structures or people? And then also to come to this goal, there are a lot of technological problems on the way. To be solved, what technologies to use, how to make them safe. Also these questions of having fail-safe systems versus fail operational systems. So systems that have to continue to work even if things go wrong. And that's a plenty of problems that are there.
Right. So what are the different limitations that each type of a vehicle presents? Is there anything that is uniquely different in some of these?
Yeah, when we take it from a broad view, then probably for each type of vehicle we have use cases, what this vehicle shall do. And coming from these use cases, then different constraints apply. So what you already mentioned, technical constraints on the size of the vehicle gives me a constraint of how big can the technology be that I want to install there, where a big truck gives us much more space to install things, while a passenger car has much more limitations. Also from the use case point of view, if I want to build an automated delivery truck which drives a certain route, let's say through the US, East Coast, West Coast, and I can say the constraint is it will always use the same streets. That's also a constraint that you can use when you build the system and say, okay, I don't have to train it for other use cases than that one. Yeah, so these kind of possibilities are there, yeah.
And before we get to autonomy, I presume that from a technology perspective, there are a lot of other things that need to come as building blocks before autonomy can really exist. Can you talk about what are the things that are happening now that are going to enable autonomous vehicles in the future?
Yeah, basically, when we go back from the future in a little bit of the historic timeline, looking back in the 80s, early 90s, or even the late 70s, when we moved from pure mechanical systems to electronic-based systems. So fuel injection as one of the first things that came up. And here always the question came up about how can we ensure that this is reliable, that this is safe, and so on. One remarkable point, I think, here was in the 90s when we switched from the mechanical accelerator pedal to the electronic accelerator pedal. Because at that point in time, there was no way that you could mechanically limit the power of the vehicle. That means in the worst case, the vehicle could apply full power to the wheels. And depending on how much power this is, the driver had more or less good chances to cope with that situation. So while you had a mechanical safety system where you could say if you take off the foot from the pedal, then the spring load will pull the throttle to close and then the power will be gone. This had then been replaced by pure electronic means. These electronic means enabled a lot of innovation. So from that point on, we could build a new generation of combustion engines because we now had more control over the parameters and so on. So I think this is a very interesting element here to understand, coming from the history, that we build slice by slice, or we build on puzzle pieces, yeah, and build on this safe method to control the power, yeah, enabled us then to develop, for instance, the cruise control in a new way. From the cruise control added with radar, we could come to adaptive cruise control. And so everything builds on previous steps. And I think this is what will continue for autonomous vehicles, that we have building blocks that we pile upon each other to then finally come to the solution of the autonomous vehicle. And this works already quite well for certain constrained use cases. And it's a continuous hunt in the future to improve, to enhance these use cases and getting more and more into the full autonomous picture here.
Right. So that's interesting that we are essentially standing on the shoulders of giants. So as we develop newer technology, there are a lot of things that have happened in the past that we're building on top of. And there's a lot of incremental innovation that's happening. So you talked about electronic control over power that a vehicle generates and kind of how getting that control through electronic means is one of the building blocks to autonomous vehicles. But today there are drive-by-wire cars, right? Like actually not today, probably for the last decade or more. These cars are completely controlled by wire. Is that something that you see as a prerequisite, in the sense that the drive-by-wire cars today are not the cheapest models out there? If autonomous vehicles are to become universal, then the cost and all of those things need to be driven down to make some of these technologies available to every car. Are there advances being made in that as well?
Yeah, I think that's what we see, as you mentioned, with the steering. So today, most of the cars still have a classical steering column, but we have an actuator sitting on top of it, which can then control the steering angle. You could imagine that you could even get rid of the steering column and have then a system which has no steering wheel at all and just actuators directly on the wheels, which probably is one of the visions when we look at these future taxis, which have basically only passenger seats and no driver seat at all anymore. But the way forward is basically that at the point we are, especially in the automotive world, we still have to keep the driver in the game. Yeah. And that means also certain cost is involved to have this more complex steering. And then usually it trickles the way down. Most of the OEMs introduce new technology on their high-priced cars. And then over time, it will trickle down to the smaller models. And that's also because of volume effects. By producing it, by making more and more volume, you get it cheaper. And that's probably the principle we see here that will also happen for the assistance systems. Basically, we've seen this already. When we look back in the 80s, the ABS anti-blocking system for brakes, there was at the first introduction a system only for the higher segment cars. Today, it's an completely obvious system that every car has, and the same we see with driver assistance systems currently. The other thing is that also when we switch to, let's say, electric vehicles, things would probably get cheaper because of the powertrain. That we save money because we get a much simpler powertrain. But then still have to invest that money probably in the development of these advanced assistance systems.
So all of the stuff we talked about is kind of inside the car. Are there things that are happening outside the vehicle which will help with getting us to an autonomous future? Yeah,
that's basically what my team is currently looking into. That's the topic of this reliable distributed systems, how we can build reliable, safe systems that are composed of probably a vehicle and an environment. A very popular example here is called infrastructure-assisted driving. Bosch just released a system called automated valet parking, where you can just put the car at a location and then tell the parking garage, please park my car. This is kind of such a system. And we see when we look into research papers that there's lots of things ongoing with so-called roadside devices that are basically sensors that can provide extended information to the vehicles. And it's likely that for certain use cases, we also see this combination of in-vehicle technology plus external technology as an accelerating measure for autonomy.
Yeah, excellent. So we see a lot of changes happening inside the vehicle as well as now outside the vehicle. But where's the brain? So we talked about a lot of these things requiring intelligence. In your mind, where's the brain of this thing? Where does the brain sit? What does it do? What's the kind of compute that we're going to need to have these autonomous vehicles running around on the streets?
The brain, yeah. When we say the word brain, we quickly come to the term of KI and or AI, and it's then usually neural networks or things like that. And I think this is one central element. AI technology, machine learning is one element to get this realized. But it has a lot of different aspects, in fact. The biggest thing, I guess, is that one question is about the functionality. What do I have? What do I need as a brain to achieve a certain functionality? Drive along the lane. Yeah, we are quite good at that already. But the second big question that comes up is, how does the system find out that it's still doing the right thing? So is the system aware of itself if it sees the right data, or if the data is corrupted and can then act also on this? So this for the scope of what this brain has to do. It's not only being aware of doing the right thing, it's also being aware of what's going wrong. And can I still do the right thing even when these things are going wrong? So in a very abstract way. And yeah, what we see on a technology space, yeah, we see a lot of this deep learning topics, acceleration. When we do neural networks, certain types of neural networks, and we run them on general compute platforms, then we see it's power intensive. So we try to build special accelerators. And with these special accelerators, we can then get the power consumption down. And so this is currently one of the things for this, let's say, brain development, that you need to have the right technology to do the functional stuff, to the right technology to do the, let's say, non-functional and safety elements. and then also be in the constraints of power and size for the whole system. Because on a vehicle that runs on batteries, you want to use not most of the battery power for the computation. You still want to use that for the powertrain. And this is a multidimensional topic here in designing this, and very challenging. And that's exactly what the industry currently faces as the main thing here when we are moving forward to get these systems really defined and it's a continuously evolving discussion currently.
So if you look at the brain of these things, we talked about a lot of these decisions that are being made, inside the car. But I presume some of these decisions can be made outside the car. You'll have some parts of, for example, the planning or the mapping that happens outside. Then you'll have some parts that locally are optimizing for short-term planning and so on. And so you'll have compute. I think you talked about one of the phrases that you used earlier is distributed computing. So in a lot of this decision making, architecturally, it looks like a lot of different compute units that are collaborating and trying to get us to a safe outcome rather than like the one big brain that's deciding everything. Would that be a fair assumption?
Yeah. Speaking from that brain, what we currently talked about with a pure in-car focus, the reality, you're absolutely right. It's that it's not only what we have in the car, it's also the surrounding. And then again, in what scenario, in what use case we are doing this. There are scenarios that you can imagine where a vehicle can be autonomous within enough constraints and you don't need much of an outside interaction. But the closer you get to a fully autonomous vehicle that can act completely on its own, then there is the question, can you achieve this with all the data that you just gather with the vehicle itself? So it's basically a question of what information you are able to acquire. And when we imagine a vehicle that has radar and LiDAR and vision, then with these inputs, you can get certain amounts of data. From that point, where are they located? But when you add the infrastructure, then you can give the vehicle much more data because the infrastructure knows much more about the environment. And I think this makes it quite plausible that when we want to reach fully autonomy in all scenarios, especially in crowded urban driving, then it's very likely that we are looking more in a distributed scenario where the vehicle is one element of a more complex overall system.
So there's not only distributed computing problems, but you're also talking about a deluge of data that is coming at these systems to not only make decisions in real time, but also through the training process. Can you talk about what does that loop look like in terms of, let's start with the in-vehicle loops in terms of how it reacts to data, that's all of this data coming in, and then we can zoom out to the training.
Yeah, basically, I think we have to differentiate between those things that we can solve without having the need for machine learning. So there is several technology, for example, LiDAR. If we want to know the distance from an object, LiDAR works quite well under certain conditions. And here we could work even without machine learning for simple approaches here. But then when we come to vision processing, so that's where it really gets interesting. So yeah, at the end, the vehicle will be able to get the data through the sensor of the camera. And then you have to run through a lot of different steps of post-processing. So one thing is basically to identify objects on that picture, but you also have to first find out if you can trust that picture at all. So let's assume it's raining and you have this camera mounted in the windshield. So now you have raindrops in front of the camera. So now you get nice effects on your pictures. And that's also important that the camera now recognizes, oh, I cannot trust these pictures anymore. So I'm not allowed to do the calculation on that. So that's usually why it's then important that you have a wiper that cleans the camera and so on. Or let's take other things of dirt coming up. And yeah, that's first steps is really finding out, can I trust the data that I have there? Is this really processable data? And then you go through the post-processing where you basically then analyze what's in the picture and so on. And so forth. And then getting all these different sensor data through sensor fusion aligned with each other, which is also quite tricky because, all of those from computer science know distributed acquisition of information. You must time synchronize then all these systems and to be able to align all the data with each other. And then you can finally come out with a result. So that's the minimum loop to, let's say, follow a lane would be then taking the data fusion, coming to a planning decision, and then steering the actors in the right way to keep the lane. But especially when we talk about vision processing, you have a real long tail in the chart of possible scenarios. There's so many scenarios that could be out there, and that makes it then important that you can have development tools that enable you to continuously improve the vehicle. So then we leave the vehicle space. So we have to submit data to the cloud, for instance, of certain situations to be able to analyze them further and probably retrain the networks that we have to cope with that situation. And then it comes back that we have to update the vehicle at some point with this updated information to be able to cope with the situation. And then it's, let's say, already a quite advanced, we call it the data loop development environment. And that's exactly what ETAS as a company is working on, such kind of development tools that support then the developers for developing these kind of systems with data acquisition, data analytics, and also then continuous development and deployment into the vehicle. That's, let's say, that's the starting point of this huge topic,
Yeah, absolutely. It sounds like just thinking about what are all the things that need to happen. A lot of them happen in loops. So you have the sensor actor loop. We talked about the powertrain loop between positive momentum, negative momentum in terms of the adaptive cruise control that you talked about. That's kind of how you would control whether you want to move forward or backward. And plus the data loop and the development loop and the feedback loop and so on. So there is a lot of loops. I find that quite apt for the vehicle where you have the tires moving forward all the time. So you have all of these loops moving us forward in this context. One of the things you touched upon early was safety. And we know that safety in this whole world of automotive is absolutely critical, not just because of, we all want to go in these cars and we don't want to do something that risks our own lives, but also from a compliance perspective. You cannot actually sell a car unless it complies with certain regulations, ISO 26262 or other. Can you talk a little bit about what are the things that are being done now to make these autonomous vehicles safe and compliant?
Probably it's the biggest topic overall when coming to this world of automation and electronics. At the foundation is always the idea that you have to argument why it is safe. So when you develop such a system, usually the idea from a regulation point of view is to get an acceptance, you have to provide an evidence chain on how you made the safety guarantees. Yeah, let's probably start with a very simple example from the 90s. When you have a car with an automatic gearbox, which is also electronically controlled, then there could be probably a situation where the electronic malfunctioned and triggered the different valves in a way that you had blocking wheels. And then the question comes up, okay, if this can happen, so what are possible outcomes? And blocking wheels, you have to differentiate if it's the front wheels blocking or the rear wheels blocking. At the end, you come to a reaction time. You have to resolve the critical situation in a certain time span. And then you have to build the system and the evidence chain to show that given on that analysis, that this is the scenario that can happen. You have done these steps to ensure that it cannot happen. And if it happens, that it's resolved within the reaction time so that you are still safe. I think in blocking rear wheels, it's less than 500 milliseconds or so that you have to resolve the situation, which basically means you have to bring the gearbox in the neutral gear. And then you see it's not only a software problem, it's a hardware-software problem, because also the hardware designers have to take into account, okay, there must be, the neutral state must always be reachable also when the electronics fail, and so on and so on. So you come into a system view. That's a very important understanding. It's not only software that makes things safe, it's always the system that must be safe. So that's hardware, software all together that must work here. And yeah, when we go on for autonomous vehicle, we can just continue. What's about the steering angle, how you can protect that there are no malfunctioning inputs, that you get a 90-degree angle suddenly. And here also you have certain analysis that say what rate of steering is allowed and acceptable, and you can implement monitoring to ensure that the software doesn't output levels about that or react when it's happening, and then get into a fail-safe mode, and so on and so on. Interesting it gets when you come to this fail operational question, so that you have then to ensure that even when such things happen, you are still able to continue. Then we are talking about redundancy and these topics that we have the need that systems are multiple times available. And complexity explodes really when you go into that, because when you go from this redundancy question, then it means, okay, you need 2 times the computation, 2 times the power supply, 2 times the buses. So you need to at least double the effort and so on. That's some aspects, some glimpses on how this works to make it safe. I know the guys in my team who focus on safety would now have thousands of more arguments and details here. So I'm can only abstract it. But I think the main point is a very structured and systematic way to develop these systems. I think that's the main point. Because at the end, I'm coming myself also from the IT, from the software world, not being born native into the embedded world. And I know in the IT world, we are very pragmatic. We code first, we just write something, and then we see how it works. In the safety world, you always have to think about, I write now something, but how do I argument why it's written that way? And if I do that at the end of the development chain, it will be very, very painful. So developing autonomous vehicles really is about also a discipline and systematic approach on writing software or developing hardware all in the same way.
Yeah, absolutely. One of the things that I find personally very fascinating about these safety things. So this is one thing that I think would be very entertaining to be in, but not very fun to have to be in. And it's the limp home mode. I find that to be very fascinating, because it would be very interesting to be in a car which is just limping home, because that's you are out at a pub, you want to come back, and as a driver, you're essentially just trying to limp home. But there are situations where the car is trying to limp home. And I find that to be very interesting, because even if you have to limp home, you still have to get home. So there are a lot of things that the vehicle still needs to do, but it's obviously in a disabled state for some reason. And so when you talk about fault tolerance and redundancy and all of these things, so at some point, the vehicle needs to continue to operate to some level of not only safety, but functionality, even when, all kinds of things have gone wrong. Maybe somebody's come in and hit your car. Maybe the road conditions are unsafe. Whatever other reasons there may be. Would you say that is that a harder thing to do than when everything else is working fine? Or is that, as a fallback mechanism, is actually simpler? Yeah, basically, the idea of limp home is always an idea of degradation. So you have not the full system functionality. We even have that today on combustion engines. If things go wrong, then they go in a power degraded mode, and you can barely drive 50 kilometers per hour and then come home. For autonomous systems, I think it's also quite complex, because on one hand, you have to decide at a point when it's time for the limp home mode. Yeah. And there are multiple cases. You mentioned it. There could be a crash. It could be a failure on the system itself. It could be a loss of redundancy and so on. And then you have to analyze the situation that you are in
And let's say if you're on a motorway, then probably the limp home could also be an emergency stop on the emergency lane, so that the vehicle is able to go to the emergency lane and then stop there with the warning lights on and things like this. The other question is, what is when you are in a really complex situation? Yeah, let's say you are on a crossing and your car has been hit, probably rotated. So now the system has to find itself in a completely new situation and find a safe way out. And here it's about the question, okay, what is the safety scenario? So what is the safe scenario that you are heading there? So probably after a crash, you won't drive that much anymore. You probably only go to a location where you are more safe. But I think it's a lot of design questions that are still open here, how this can be solved. And also, let's say we are learning this information also from vehicles in the field that provide that data, that have crashes, and where we can see how a crash behaves, what happens. And then it's also a lot about probability. What are probable scenarios that may happen very often? What are improbable scenarios or very less likely scenarios that happen only 1 in 1,000, 1 in 100,000, 1 in a million times? And then also have the right effort for the right topics. Probably what happens most often, you have to have the solution for.
Yeah, absolutely. We talked about several different types of things within autonomy. We talked about being in the same lane. We talked about adaptive cruise control. And then we talked about, going across the East Coast or East to West in the US, or parking. We talked about the limp home mode and all of the things that happen. How do you drive autonomously in a complex situation that you never encountered before? Can you help put that in a framework? How do you think about it? Because all of these are not equal. Are there ways to classify them? Does the industry have like a standard way to classify these things and say that this is what we mean by autonomy at this level?
Yeah, basically the SAE has defined these levels of autonomy, which have become the de facto standard, I think, around the world for the classification model. So where we have these levels 0 to 5 to classify the different types of systems. Where, for instance, level 0 means basically you have no automation on the driving at all. You may have warning systems like emergency braking or lane departure warning, things like that. Starting with level 1, then you have really driver assistance, where the driver gets assistance from a system, but it's clearly defined. The driver is driving the car, not the computer. Then it goes up to level 2, where you have already partial driving automation. That means you could have an adaptive cruise control plus a lane keep assistant. And if you run those at the same time on a motorway, then you basically can take off your feet off the pedals and you can take off the hands off the steering wheel. And then the car will seem to drive autonomous, but basically it's just keeping the lane and just adjusting the power that you keep the distance to the front car. It will not be able to cope with certain situations, and at that point also you as the driver are still fully responsible. And that's usually where also the vendors ensure that if you take off the hands from the steering wheel for too long, they will give you signals, and then they will also leave the automated or this partial driving automation mode, because you are still the driver. Yeah, up to level 2, this definition says there's the driver, and the driver is driving the car. And then starting with level 3, we enter the world of autonomous driving, or let's say automated driving. So it's not fully autonomous; it's has driving automation, where in level 3, the vehicle can still give back the control to you with a certain time span. I think it's around 10 seconds or so. So the vehicle has to tell you, I'm not able to continue, please take over again as a driver. And then it hands back the control to you. And that means the system at that point must be able to find out when it's not able to fulfill its purpose anymore, and then actively hand back the control to the driver. And then starting with SAE level 4, it's basically that the vehicle must cope with the situations with certain constraints. So you could say, yeah, it's only working on motorways and nothing else. Yeah, that you could fully automate it, run on motorways. And then when we go to level 5, then it must be able to do to cope with all situations. So that means up to level 3, the driver must always be ready to take over. Starting with level 4, then we talk really about systems where you could do other things, don't have to take control. And with level 5, we are then at this robo-taxi level where you just sit in the car and the car brings you from A to B and you don't have to interfere at all with the vehicle. So this is the standard in the industry that we use to classify the level of autonomy that a vehicle has, and where you classify most of the vehicles that are on the market today into.
Where are we today? What level do you see most of the cars that are on the road today? Or at least the most advanced cars on the road today?
I think the most advanced cars are between level 2 and level 3 as general purpose passenger cars. There may be higher levels with bigger constraints. There's automatic robo-taxi services, but they are geo-constrained. They are only working in certain areas. So that's then higher level, but it's with the constraint, and it's only for a certain purpose. It's then a robo-taxi. But when you ask me for passenger cars that you can buy today as a driver, then we are between level 2 and level 3. I think there's not so many certified level 3 systems available that are really certified. I see a lot of level 2 systems that try to have all the features that a level 3 system has, but they are not yet fully certified. So my car, for instance, has a lot of the level 3 features, but it can hand me back the control within less than a second. So it does not tell me, could you please in the next 10 seconds take over the control? It just says, now you need to take back control. And that makes it a level 2 car, even if I can drive for certain distances without driving at all. So when I go home from work, it drives a lot on itself, but in certain conditions, you really see then the system is not capable for all the situations, and then really tells you, so now I'm not knowing how to handle the situation, and I hand back control to the driver.
Wow, yeah. So being inside the industry, and you're in the middle of making all of these things, which level do you think is going to be the hardest level to get to? Which jump? 2 to 3, 3 to 4, 4 to 5? Which jump do you think will be the hardest?
I think it's currently the 2 to 3 jump, which is currently ongoing, and where in the last 5 years, I think we saw a lot of progress. I think that's really the big jump because on the one hand, the understanding on how to build these systems. So it's let's say possible to build a system when you get enough compute power. So you take racks of computers and then say, now I have a level 3 system. But then you have to integrate it into your car. And then you find out, all these racks are not fitting into my car. That's a problem. And that means that probably technologically we have already some things reached, but then the integration process into the vehicle has also to be fulfilled. And then you have to certify the vehicle at the end. Yeah, you cannot tell the certification, look, that's the vehicle, look, that's the rack, please certify me the rack, and trust me, I integrate it later in the vehicle and it will look exactly the same. Yeah, that does not work that way. And so I think that's where we are currently at this jump, and that's probably the most interesting time currently to see this evolvement currently ongoing. Yeah,
I love that picture. Where we are today is there's a car, and then there's a big rack of compute that's sitting outside that can make the car go autonomous. And now the problem that we have is, how do we take this rack and fit it inside this car and still, get it to do its things and get certified? As we move into the future, we described kind of the 2 to 3 jump as being where we are. What needs to happen? Like, what needs to happen between where we are now to this future? Are there some meta themes that in your mind are the things that we as a community kind of need to do going forward?
Yeah, the big question that I always ask myself is what use cases are the most important ones currently. Yeah? I think to have an autonomous vehicle, to buy it and have it, it's one aspect. Yeah. But I see a lot of potential, for instance, in the logistics area. Yeah, where we could, you probably read the news. We have a shortage on truck drivers. Yeah, it's one of the things where I say, okay, one thing is we get more truck drivers. The other thing could be we have autonomous trucks faster, so that we could automate that part of the logistics chain. So the question is really what topics are the interesting ones that we need to address first. Very interesting, I think, also is the agricultural area. When you have large fields that you have to process, and here we already saw over the last years a lot of progress because the safety is not as complicated when you have quite slow driving systems. And agricultural automation, I think, is also a very important use case from a community point of view. Yeah? So I think that's the question when we go for self-driving passenger cars. When we look here in Germany, for instance, I think about we have this demographic change, so people getting older and older, and we have less young people. So then it's probably an interesting question. Would it help older people to have, let's say, more autonomous life because they are still able to get from A to B without outside help because they can just use an automated system, a robotaxi or so? I have to be careful because all the taxi drivers in the world would probably not like the idea that they are not needed anymore. But you see, that's from my point of view, the interesting question about the community. What are the real use cases from the benefit? And when we look from a commercial point of view, what are the use cases then at the end where people are willing to invest because they see there's the return of invest at the end? Yeah. I think that's, from my point of view, the big question around autonomous technology at all. What does it help? Where does it help? And who's wanting to implement that?
Great. Thank you so much for taking the time. And with that, we come to the end of episode 1 of the Architecture of Future Technology podcast. I leave the audience with a wonderful image that Joerg presented us, which is if you're driving an autonomous car today, there's probably a big rack sitting outside. Now the challenge is how do you fit that rack inside your vehicle? And Joerg's answer, the initial stages of this, maybe you should be driving a big truck or an agricultural equipment in which you do have the space to fit in the compute. So I think I really like the image and the kind of the immediate next steps that seem feasible. Thank you, Joerg.
Thanks for having me.